Hello all, we are moving to the next lecture in Raman Spectroscopy, Rotational Vibrational Raman Spectroscopy. We need not consider in detail the rotational fine structure of Raman spectra in general because the rotational fine structure of Raman spectra is resolved only in the case of diatomic molecules. So we are considering rotational vibrational Raman spectra in case of diatomic molecules only. We can write the rotational vibrational energy levels as a function of vibrational quantum number V and rotational quantum number J as epsilon JV equal to V plus half into nu bar E minus V plus half the whole square nu bar E chi E plus Bj into J plus 1 centimeter inverse. Here we are combining the rotational energy with the vibrational energy levels of an anharmonic oscillator, where V and J are the vibrational and rotational quantum numbers that can take values from 0, 1, 2, etc. Nu bar E is the equilibrium vibrational frequency, chi is the anharmonicity constant, and B is the rotational constant. Next, we can apply the selection rule to the energy level expression to obtain the transition energies. We know the selection rule for rotational Raman spectroscopy is delta J plus or minus 2, and for vibrational spectroscopy it is delta V equal to plus or minus 1 plus or minus 2 etc. Anharmonic oscillator. Here we are combining the rotational selection rule with the fundamental transition, that is V equal to 0 to V equal to 1, which is the only probable transition with sufficient intensity. Here, there are three cases. First one is that there is only vibrational transition, that is the change in rotation. There is no change in rotational energy level, only the vibrational levels are changing, so that delta J can be 0, and we get something known as Q branch. The lines are known as Q branch, and for this the wave number is nu bar E into 1 minus 2 chi E, which is the fundamental transition, fundamental absorption frequency. Then there is a possibility that delta J can be plus 2, that is the absorption transition, where J 0, 1, 2 etc. 0 to 2, 1 to 3. For that transition, we will get an S branch of lines where the frequency is nu bar E into 1 minus 2 chi E plus B into 4J plus 6 centimeter inverse. This is the frequency of the transition, and the frequency increases. Then we can have another branch for delta J equal to minus 2, that is the emission transition from 2 to 0, 3 to 1, 4 to 2 etc. That is J can be 2, 3, 4 etc. where we will get O branch, and that having frequency nu E bar into 1 minus 2 chi E minus B into 4J plus 6 centimeter inverse. Therefore, the rotational vibrational Raman spectrum will contain the Stokes lines, that is the lines to the low frequency of the exciting radiation, and it will occur at wave numbers given by nu bar Q equal to nu bar excitation minus delta EQ. Next is nu bar S. Next is nu bar O. All have a decrease in frequency from the exciting radiation, where we know delta EQ is that, and delta ES and delta EO. Then we have another branches, another set of lines known as anti-Stokes lines. What can be the frequency there? It will be nu bar Q equal to nu bar excitation plus delta EQ, thus increase in frequency from the exciting radiation. And where also we can get nu bar Q, nu bar S and nu bar O. That is, we can have in the rotational vibrational Raman spectrum the Stokes and anti-Stokes lines appearing at either side of the exciting radiation, and it can have the equations nu bar Q equal to nu bar excitation plus or minus delta EQ. Here also can be plus or minus, and plus or minus. The plus sign indicates anti-Stokes lines and the minus sign indicates Stokes lines. So here you can see a rotational vibrational Raman spectrum. These bunches of lines will appear at either side of the exciting radiation. Here O, Q and S branches are shown. The presence of strong Q branch in the Raman spectrum is to be noted, and can compare with the P and R branches only which occur for a diatomic molecule in IR. The analysis of the O and S branches in the spectrum can provide us the value of rotational constant B, and once we know the value of B, we can get the value of moment of inertia by which we can get the bond length. Now we are comparing the IR spectroscopy with Raman spectroscopy. Both IR and Raman spectroscopy are types of vibrational spectroscopy. IR spectra works by the detection of light scattering, known as Raman scattering of monochromatic light, usually visible near in IR or near UV range. IR works in the infrared region. The Raman spectrum measures the relative frequencies at which a sample scatters radiation, but the IR spectrum works by measuring how much light is absorbed by the bonds of a vibrating molecule. Raman spectrum detects the polarizability change of a molecule, while IR detects the dipole momentum change of a molecule. So, the dipole moment change of a molecule. Thus, some vibrations that are active in Raman may not be active in IR and vice versa. An advantage of Raman spectrum is that there is no destruction to the sample in Raman spectroscopy. In IR, the sample needs to disperse in transparent matrix. For example, we have to grind the sample in solid KBr for the analysis. Solid KBr means potassium bromide. Raman spectroscopy can be used in aqueous solutions, while water can absorb the IR light strongly and affect the IR spectrum, so that water cannot be used as solvent in IR. The key advantage of Raman spectroscopy is that it requires little or no sample preparation, while the IR method has constraints on sample thickness, uniformity and dilution to avoid saturation. So, IR technique is more time consuming than Raman technique. Homonuclear diatomic molecules are all IR inactive. Fortunately, the vibrational modes for all homonuclear molecules are always Raman active. Raman spectrum also has some disadvantages, that Raman spectroscopy is a much more expensive technique to use than IR, since high-powered lasers and amplification sources are needed to get sensitive results. The key advantage to IR is the difference of the two methods in dealing with interference. Fluorescence may interfere with the ability of taking Raman spectra, which would not be an issue with IR. So, whether you are using Raman spectrum or IR spectroscopy, both methods have advantages and limitations. But when combined, these two methods become a powerful tool when performing material characterization. Thank you very much.